Hello, this is John Hearn, and we're going to be looking at solving some old Physics 1 exam questions that cover conservation of energy and linear momentum. All right, so this first question, we're throwing a 10-gram coin at 5 meters per second at an angle of 45 degrees above the horizontal from a 60-meter tall bridge. There's two parts to this question. One is how much work does gravity do by the time the coin reaches the water below? And part B is what is the speed of the coin just as it hits the water? All right, so with any of these questions, we're going to start by just sort of sketching out the problem. We have an initial speed of 5 meters per second, and this is at 45 degrees above the horizontal. And this is on a bridge that is 60 meters tall. So we're starting off at 60 meters, and the coin is going to go all the way down and eventually hit the ground. And so here's the problem space that we have. Now there's 2 points of interest that we are interested in. The release point, which is at 60 meters above the ground, the water, and then the water. Okay, so we can look at both of these points. So for this first point, we're going to just outline what we know at this point. We know that the gravitational potential energy at this point is mgh initial. And we also know that there's some kinetic energy at this point, which is 1/2 mv initial squared. All right, and now what we also know down here at the bottom that the gravitational potential energy is 0 at the bottom because we're going to let that be our 0 point. So down here h equals 0, up here h equals 60 meters. So that's going to give us a final potential energy of 0. And then we're going to have some final kinetic energy like this. All right, so we're just kind of mapping out the space. And then let's go back to the problem statements. Okay, how much work does gravity do by the time the coin reaches the water below? So this is asking about just the work that gravity is doing. And recall that the work that gravity does is equal to negative the change in potential energy of gravity. Okay, so this is the definition of potential energy for a conservative force. Let me try to focus that a little bit better. Okay, so we can simply substitute in what we have here. This is negative UG final minus UG initial. And then we can plug in what we're given. So for part A, we know that we have our final potential energy is 0. Our initial potential energy is mghi. So this is going to equal mghi after we cancel our negatives. And so we can plug in our mass, which is 0.01 kilograms. Gravity is 9.8 meters per second squared, and then the height is 60 meters. And so then the work done by gravity, after we punch that into our calculator, we're going to get 5.88 joules. And this is a positive quantity, as we would expect, because gravity is doing positive work on it as it falls to the ground. All right, so then for part B, what is the speed of the coin just as it hits the water? So for this part, we want to look at our conservation of energy equation, which is that the work equals delta K plus delta U plus E thermal. All right, now we can account for the work of gravity either right here in the potential energy term, or we can put it over here and say our potential energy is 0. It does not matter which way we go with this. If we put it over here, then this is a negative 5.88 joules. If we put it over here, it is a positive 5.88 joules. So just for the sake of this problem, we're going to put work over here, meaning we're not actually looking at any potential energy change, and we're not losing any thermal energy because drag is not part of the problem. So then we know that the work done is the final minus the initial. And then if we look back up here, I know the initial is 1/2 mvi squared, which is 5 meters per second. And then the final is what we're looking for. So the rest of this is just plugging in what we know. So we're going to plug in 1/2 m v final squared minus v initial squared. And we just need to solve this for the final velocity. So if we do that, we're going to first multiply our 2, divide our m over. So we're going to get 2 over m times the work. And then we're going to add our VI over. And then we're going to take the square root of the whole thing. So then we're going to plug in our numbers. We have 2 over 0.01 kilograms. The work done by gravity is 5.88 joules. And then we're going to add to that the initial speed squared, which is 5 meters per second squared. And then we're going to take the square root of that whole thing. So the final velocity is 34.7 meters per second. All right. And we know that this is actually down because of the problem. Remember that the kinetic energy analysis does not tell us the direction of the velocity. All we get is the speed, but of course the problem statement just asks for the speed. All right, question 2. A 70 kilogram student jumps off a 28 meter high bridge with an 18 meter long bungee cord tied to his feet and to the bridge. A bungee cord is essentially a flexible spring. The student's initial velocity is 2 meters per second straight up. What must the spring constant be to have the student's lowest point be 5 meters above the water? Okay, so to solve this problem, we're going to first sketch out the problem space. So we know that the person starts at 28 meters above above the ground, okay, or the water. So if we just let this be our 0 point for the height, then this height is 28 meters, okay? All right, now we have 2 other points of interest. We have 5 meters above. So this is where we want the person to end. H equals 5 meters, okay? And so at this point, we want the person to stop. So this is the lowest point for the bungee jump is where the person has turned around and is starting on their way back up. So this is at 5 meters up. And then we have one more point of interest on this, and that is the bungee cord is 18 meters long. So if we take that, we know that 18 meters from the top is going to be this is going to be where the bungee cord starts catching the student. Okay, so at this point, x at this point equals 0, right? And then this dimension right here, this is how much the bungee cord stretches, okay? So the person jumps off, they free fall for 18 meters, and then the bungee cord starts doing its work, and it does its work over this distance right here to stop them at 5 meters above the ground. Okay, so those are the points of interest that we have. Right, now we can go ahead and label our energies. Up here we have the initial gravitational potential energy. This is just mghi. We also have an initial kinetic energy because the student jumps up 2 meters per second, so the initial kinetic energy is not 0. We know that it's 1/2 mvi squared. And then we know that at this point, we do have some final gravitational potential energy. We know that the kinetic energy at this point is 0. It's 0 because this is where the student is going to stop. And then we also know that there's some spring potential energy, which is 1/2 kx squared. And then right here, we know at this point, and all the points above this, the potential energy of the spring is 0 because it hasn't started doing any work until it gets to this point. And then this is where the bungee cord slows the student down. Okay, so let's go ahead and just list out all of our knowns. We know that the mass of the student is 70 kilograms. We know that H initial is 28 meters. We know H final is 5 meters. We know that the initial velocity, VI, is 2 meters per second. And then we can find out what this x value is here simply based on the fact that this x value is 28 meters minus 18 and minus 5. So 5 plus 18 plus x has to give me the whole distance of 28 meters. So x is equal to 28 meters minus 18 meters minus 5 meters, which turns out to be 5 meters. Okay, so this is x, so we know x is 5 meters. And then just so that we remember what we're looking for is the spring constant. Let me highlight that. We're looking for the spring constant. So that is right here in this term down here. Okay, so now we're ready to assemble our conservation of energy equation. So let's do that down here. We have the work equals delta K plus delta U plus E thermal. There's no drag or frictional forces that are mentioned in the problem statement. We're going to put both the spring and gravity potential energies right here into delta U. So those terms are 0. So now we can rewrite this. We're going to expand K into K final minus K initial. We're going to expand delta U into two terms, or two deltas. We have U gravity final minus U gravity initial. And we have U spring final minus U spring initial. Okay, so in all of these terms, the final kinetic energy is 0, so we can get rid of that term. The initial spring energy is 0, so we can get rid of this term. And now we're left with 4 non-zero terms. The unknown is inside this final spring potential energy. That's what we're solving for. So let's go ahead and algebraically put it on a side by itself. Well, here, we'll do this in 2 steps. Now let's go through. This is negative 1/2 mvi squared plus mgh final minus mgh initial, okay, plus 1/2 kx squared. So again, we know everything in this equation except for k. So we can solve for k algebraically. So we can I put all this stuff over and then multiply by 2 over x squared. And then all we need to do is plug in all of our quantities. And I'm going to go ahead and factor this into just mass and gravity. And then I'm going to do HI minus HF, which is 28 meters minus 5 meters. And then we can solve for the spring constant, which I got 1273. If you work through the units on this, you'll notice that all your mass units cancel, and then you're left with kilograms per second squared, which are kind of strange units. Typically, this is expressed in newtons per meter, and a newton per meter is the same thing. So this is a kilogram meter per second squared per meter. So this is a kilogram per second squared. So a kilogram per second squared is the same thing as a newton per meter. All right, number 3. A student places her 500-gram physics book on a table. She pushes the book against a spring, compressing the spring by 7.9 centimeters, then releases the book. The spring constant is 200 newtons per meter, and the kinetic friction force between the book and the table is 1 newton. What is the speed of the book just after it leaves the spring? So let's just sketch out a quick picture of the problem. So we have the book, we have the compressed spring. It's compressed by 7.9 centimeters, which is 0.079 meters. And at this point, this is where the book is going to have its final velocity. Okay, so the spring is going to push it until we have the final velocity. And we're looking for this speed of the book just after it leaves the spring, so we're looking for the speed of the book at this point. Okay, so we can go ahead. Let's just map out our initial. So here we have everything is in the spring. So the initial spring potential energy is 1/2 kx squared. The initial kinetic energy is 0 because it's not moving. And then over here, I'm going to have the final spring potential energy is 0 because it has reached back to its equilibrium position. So x is 0 at this point. And then the final kinetic energy is just 1/2 mv final squared. All right. Along the way, we have kinetic friction. Okay, so we have to include this. So this just tells me that some of the energy is lost to thermal energy. So let's write out, and in that case, E thermal is equal to the work done by friction, which is Fk delta S. So we can now put in our conservation of energy equation. In this case, we're putting the thermal energy over here in the thermal side. If we put it over here as work, it would be a negative term because the work of friction is negative Fk delta S. right? So the final spring potential energy, this is 0. The initial kinetic energy, this is 0. So then we have, for the final kinetic energy, 1/2 mv final squared. For the initial potential energy, we have 1/2 kx squared. And then for the thermal energy, we have plus Fk delta S. All right, where delta S and X are the same thing, right? So this is 0.079 meters. That is also the distance over which friction is acting. So these two values are the same. So then what we're solving for is the final speed. So let's solve for that. So when I do that, I'm going to get this, and then let me plug in the numbers. This is 0.5 kilograms, and then I have 1/2. The K value is 200 newtons per meter. X is 0.079 meters. The friction, the kinetic friction, is 1 Newton. And delta S is, again, 0.079 meters. So once I punch all that into my calculator, I got 1.48 meters per second. Right, so here we go. Number 4, a 30-gram ball of clay traveling south at 5 meters per second collides with a 50-gram ball of clay traveling west at 4 meters per second. What is the velocity of the resulting 80-gram ball of clay? Right, include both speed and direction. So we have a 30-gram ball that's traveling south, so we'll illustrate that by downward motion at 5 meters per second. And then we have a 50-gram ball traveling west. So here it is, traveling west at 4 meters per second. Just eyeballing this, I expect the resulting 80-gram ball to be heading in this direction. Okay, so these are going to collide and go in this direction right here. So as with all of these collision problems, momentum is conserved. So I can write that the initial momentum is equal to the final momentum, where I have to break this into x and y problems. So here's my x coordinate, here's my y coordinate, and we're going to break this into x and y problems. Okay, so let's do the x problem first. So in the x direction, I have the initial momentum is pi in the x direction is 50 grams times -4 meters per second. This 30-gram ball does not have any motion in the x direction, so it has no momentum in the x direction. So this is the x momentum initial. So this has to equal the final momentum. And the final momentum is the total mass times the final velocity in the x direction. So remember the total mass, because these clump together, so we have an 80-gram ball at the end, so this is 80 grams. So we can solve for v final in the x direction, which is, this multiplies out to be 200 grams meters per second over 80 grams. Okay, and the grams cancel, and I'm left with meters per second. And this gives me -2.5 meters per second. Notice I didn't bother converting these to kilograms because the mass units cancel. There's no harm in converting these to kilograms first. It's just not necessary for this problem because I don't have any newtons that I'm trying to work with. All right, the initial y momentum is all in this ball right here, the 30-gram ball. So this is 30 grams times -5 meters per second, which is also equal to the final in the y direction, which is m total times v final in the y direction. So we can solve for v final in the y direction simply by taking this, which is -150 grams meters per second, divided by the total mass, which is 80 grams. And then I get in the y direction, it's -1.875 meters per second. Okay, now if we go back, the velocity of the resulting 80-gram ball of clay include both speed and direction. Well, I've got the two components, so remember when we're adding components together, we have the x component, which is -2.5 meters per second. And we can do this just like we did before, where I have 2.5 to the left, and then 1.875 down. So the total is this hypotenuse right here. So this is the speed. Okay, so we get that just from Pythagorean's theorem, noting that this is a right angle. And so then we can take the square root of 2.5 squared plus 1.875 squared. And then that gives me 3.125 meters per second. The angle, we can reference this angle, that's fine. So theta is equal to the arc tan of 1.875 over 2.5, which is 37 degrees south of west. So I want to make sure that I include not just an arbitrary angle, but I've got a nice diagram here that shows how the velocity vectors add together, and I'm illustrating this is 37 degrees south of west, so I'm referencing the west direction. You can always reference the east direction by adding 180 degrees to this, but this is sufficient. All right, so here's problem 5. A 2.5 kilogram object moving to the right with the speed when it experiences this force right here. What is the object's speed and direction after the force ends? So this is an impulse problem. So we have J is equal to the integral of f dt. So the integral of this is just a triangle. So this is 1/2 times -12 newtons times 0.5 seconds. So when we integrate that, we get -3 kilogram meters per second. Okay, so this is the area, this is the impulse that the object receives. So then this equals the change in momentum. Okay, so the initial momentum, Pi, is 2.5 kilograms times to the right. So this is a positive 0.5 meters per second. And then PF is what we're looking for. And just remember that delta P is PF minus PI. So we can solve for PF by saying this is J plus pi. J is negative 3 kilogram meters per second. Pi is this quantity right here, which is 1.25 kilogram meters per second. All right, and then this is equal to PF is m times VF. So I can divide this by m to get VF. And then I got negative 0.7 meters per second. So this means that it is 0.7 meters per second to the left. Okay. All right, lastly, got one more problem. Two objects in the figure are balanced on the pivot. What is this distance? So this is a center of mass problem. We're trying to solve for, because the center of mass is where things pivot. And recall that the center of mass is the sum of xi ri over, xi mi, over capital M, which is the total. Okay, so each one of these balances at its center. So the bottom bar, its center of mass is in its middle, so that's 1.5 meters. And then the little box, it balances at its center, which is half a meter from here, or 2.5 meters from there. Okay, so we have to get our coordinates right so that we can add this stuff up correctly. So x, center of mass, which is what we're solving for, the coordinate d, is we have 1.5 meters times 1 kilogram plus 2.5 meters times 4 kilograms divided by 5 kilograms. So D is equal to 2.3 meters. All right, that's the end of it. Goodbye.